we are really here, the four of us, trying to cover somewhat complementary facets of this story. And I'm definitely not a musicologist or a musician, he's not a professional musician. And we all love music, of course, but I come from an entirely different background. I'm a physicist, actually, by training, and I'm studying physicist was studying the brain in computer science, which makes me very multidisciplinary, I would say. But my connection with music is really through besides the fact that I love music all my life, is through the attempt to understand the brain. And I see music and language and behavior in general as some sort of reflection of something very, very fundamental, very basic in the way our brain is structured. And what we want to do here now is essentially some sort of a teaser to the 2 lectures that I'm going to give later on during this course. So, and you'll see immediately some immediate connections and even overlaps with the things that Ronnie said, and probably with the things that Eli and Nori will say after me. So I'm interested really in what I would call the fundamental aspect of cognition. And if you really ask what is cognition, or what cognitive processes are all about, there's really two sides to this story. One is what we call perception, or sensory perception, which is essentially receiving information through our senses, visual, auditory, olfaction, touch, whatever it is. And at the same time, using it in some sense through activity and behavior. And actually, this is so fundamental that some of us really consider life in general as defined by something which we call the perception-action cycle, or really the interaction between organisms, not only humans, I mean, actually all organisms, starting from the most primitive ones, viruses and bacteria, if you want, all the way to insects and fish and birds and mammals and, of course, humans. What defines us is really the interaction with the world around us. So you can't really think about a living organism isolated from its environment. And this picture that you can see, or similar pictures to this in many cognitive science books, really, to me, is really encapsulates the whole story. I mean, so we receive information through the environment, through what we call the sensory perception mechanisms, and we act back on the environment, either directly by moving, by talking, by producing sound and whatever it is, or by just thinking about it. Some of this interaction can be internal, even if we don't move. Like, or right now, for example, you are absolutely interacting with me, but most of you are not making big movements or sounds or whatever. Although I see it and I react to it. So this type of cycle is what we would like to call the perception-action cycle. And if you try to define it, one of the best definitions that or at least the one I like most is the definition given by a neuropsychologist, Joachim Fuster, in his wonderful book about the frontal cortex. He actually defines this cycle as the circular flow of information that takes place between an organism or the organism and its environment in the course of a sensory guided sequence of behavior towards a goal. Now, this really again is some sort of a vision, or encapsulates the whole story as far as I'm concerned. Essentially, all my life, at least all of the maybe last 20 years, I'm trying to make sense of this. And I really, in a quantitative sense, and I really emphasize the word information here, which is going to be a very important part of the story that I want to discuss with you during this course and many other courses. Of course, many of you have seen this type of pictures before. But we know that this is not a complete dream. It's not only information. So in some sense, what really flows from the environment to us, whether it's auditory, whether it's sound, whether it's photons that hit our retina, or whether it's molecules that hit our olfactory or taste system, so it's a chemical perception, or it can be just mechanical perception, like pressure waves, also sound, of course, or just touching us and so on. All these things are just different modalities of something much more fundamental, which we call information. And of course, you all know that we are living in an age, actually, almost the end of an age that we used to call the information age. And this information age has really had a very clear, rather sharp starting point in history during the 40s of the 20th century, when the concept of information was formulated essentially in two different ways. First one was in the context of communication by Claude Shannon in his work during the Second World War in the United States, actually a little bit before that, actually in the context of cryptography. And parallel to that, more or less at the same time, by Alan Turing, following Kurt Gödel and a few others, and then John von Neumann, around the Second World War again, in a very similar task, trying to understand cryptography actually, trying to decipher what do you mean by language and how can we somehow encode it or hide it from others. In really attacking this particular question, a very crisp and a very attractive definition of information emerged. And on one end it was computation, it was communication, the story of Shannon, channels and sources and codes and decoders and so on. And on the other hand, it was computation, really the emergence of what we now call computers. Both of them really emerged from an attempt to define properly the notion of information. And as we know since then, essentially, the rest of science in some sense is getting more and more under the shadow of this concept of information. Not only in natural sciences, by the way. A lot of what we used to call humanities and social sciences so on, are influenced by the power and influence of this concept of information. I also believe that the reason we are now in a position to understand our brain, or at least we believe so, more than ever before, is that this concept of information is so deeply related to the way our human brain or any brain works. And really, this story of how information flows from us to the environment and back is the key, as far as I'm concerned, to understanding how the brain works. And so when we talk about this, we actually have we think about these two branches of information flow as two channels of information, and I'm not going to define right now what I mean by a channel of information, but essentially your intuitive understanding is clear. I mean, a medium or a physical medium, usually like the air between us now, or the electromagnetic waves, or the internet, or whatever it is, through which information flows. And this channel has this perceptual side, where information comes to us from the world to our perceptual apparatus. And there's another channel which I argue actually is balanced, and these two channels are tightly linked to each other. The flow of information that comes through the sensory perception and the information which actually use in our behavior to move, to talk, to listen to music, if you want, as you'll see later on. This is what I call the predictive channel. This is actually information that comes from us back to the environment, or interacts with the environment. And we also know that the brain itself, this is something that physiologists usually don't like, because it's very superficial. But if you look at our cortex, so of course if I ask you what is the partition of the brain, and then Ronnie actually mentioned it already, most of you will say left and right. Yeah, okay, actually it was right and left, but left and right. And of course it's absolutely true. We are more or less symmetric, and all our biological body, including the nervous system, is more or less divided symmetrically. There are many good, nice, interesting, and sometimes completely wrong stories that you can hear about the difference between our left and right hemispheres. But actually, as far as I'm concerned, at least, the more important division or partition of the brain is not left and right, but frontal and dorsal, front and back. And it's really this division between the blue and red part of the brain in this again picture taken from the same guy Puster, is that the back part of our brain, largely speaking, very coarsely and we're talking here about the cortex, only the really very late phase of our nervous system evolution. Only in mammals have cortex. Is largely active in relation to what we call perception, visual perception, auditory perception, language understanding, and so on, many other things. And whereas the frontal part, starting from this part in the middle of our cortex, the Ripley fault right here, is more or less the somatosensory cortex, is more or less dealing mainly with what we call behavior, decision-making, planning, and acting towards the future. So essentially, this is more or less the perceptual brain, and this is more or less the executive brain. Now, this partition is actually very profound in terms of this cycle of perception and action, because really, if we look at, this is the left hemisphere as you see it here. If you look at different areas here, and we're going to touch it further in the course maybe. So this is the famous area 17. This is famous for those who heard about it. And the area that is related to what? Primary vision, the primary visual cortex. This is the first place where the vision, the image from the retina, which is more or less for the context of this talk, acts like a camera, pixels that move to V1 here, and then eventually in some bottom-up process, this image is processed and filtered, and we don't really know how, but we assume that somewhere here in V, I don't know what, 5, 6, 7, 8, somewhere in the higher layers and higher levels of this information processing system, concepts emerge, and I'll come back to this. So this is the vision. There's another very important area to us right here, 41, 42, 43, 44. Who knows what this is? In the left hand side. Language. This is the Broca area, which is essentially more or less associated with language, or with at least what we call the grammatical or the syntactic aspect of language. And we know this because when this area is damaged, it's actually more motor than perceptual, but it's really lying on the boundary. When this area is damaged, we know that we have aphasia in the Broca area. We have problems with forming sentences, with using syntax, not necessarily with understanding, with speaking. It's really with understanding speech, but with forming. There's another area right here, which is known as the Wernicke area, which is related to the perception of language much more only. And we know this, of course, by lesions in the facets, but by damages, essentially. We also know that this area, the Broca area, is highly connected with music. And we'll show you some evidence for this later on, I'm sure. So we know that when we hear music, something like grammar and syntax operate. But notice that in the context of my story, that this is also related, it's really on the boundary of perception and action. Something happens in between on this interface. Just as here on the motor somatosensory cortex, there are muscles that are related to every part of our body that react to every touch or every pressure on our outer surface, which is really a little homunculus, a little map of our body on this area on both sides, both the active and so on. And when we move further into the frontal, the higher level frontal cortex, we see things which are related to larger and longer cycles like this on longer and longer time scales. So if you think really, there's a hierarchy of cycles of perception action cycles, which is again reflected not only in our behavior like motor planning, when I speak, when I move, anything that I do has to take into account further and further and longer cycles like this. But of course, music is reflecting again the same type of hierarchy, and we'll come back to this, like just as language itself. I mean, words, phonemes, words, sentences, paragraphs, and so on. There's a hierarchy of meaning. There's a hierarchy of cycles, which really is very similar to this past-future hierarchies of perception and action. So what I'm going to talk about is really trying to understand, and we know, and I hinted at this already, that a very essential component of this cycle is what we call prediction. I'll obviously elaborate on this much furthermore, but we know that intuitively, for every one of you, prediction, or looking into the future, if you want, or acting as if we predict what's going to happen, is really an essential, I would say. We cannot do anything without some sort of prediction. I cannot move my feet without knowing or predicting that the floor is going to be there. I predict that you're going to be here in the next 10 seconds, maybe even the next minute, and so on. And everything that I do is based and aimed at some sort of prediction of the future. So I don't have to even explain it to you, but essentially everything is to do based on prediction. And of course, the reason we enjoy music, and we'll come back to this, of course, is somehow not because we were evolved to enjoy music, I don't believe in this, but because music is is using or is built upon this fundamental ability to make predictions and to enjoy, in one way, this balance, this delicate balance between predictable and surprise. And we'll come back to this theme later on in my talks and other talks. I just want to talk a little bit about perception. I don't know how much time I have, but probably I'm over my time. But again, if we think about this miracle in vision in this case, how is it that this collection of pixels on our retina, which essentially is meaningless, it's just a collection of gray pixels, I mean nothing there. What happens in our brain between this image on the retina and what we call the conscious percept of a dog? How does it happen? Of course, this is one of the big riddles of brain science. I mean, what do you mean by understanding or perceiving something? And similar things happen with music. I mean, we perceive sounds on very small bits, and we'll talk a lot more about it in the context of music. And at some point, we have some bigger percept of music. What do I mean by this? Some of us at least have this. And again, so we know now that it cannot work this way. I mean, from the pixels to the object. I actually skipped one slide here, which I'll come back to. We know that there's something which we call reverse hierarchy. Essentially, we more and more believe, at least I believe, and a lot of other neuroscientists believe, that we do a somewhat reverse process. We first guess or predict that there is a dog there, and then we go back and check, do hypothesis testing, rather than generative modeling of a dog, which could be many other things. We guess based on some other things, on context, on background, on history, on culture, on many other things, that maybe there is a dog, and if there is a dog, all I have to do is to make a test of a very few items, like nose, size, color, ears, who knows what. But very few. So it's a lot more efficient, infinitely more efficient, exponentially more efficient to do hypothesis testing, first guess, and then test. And since we know it's true for vision, or at least a lot is true for vision, we also assume that it's true for audition, and I'll let Ellie maybe say a little more about it. So we actually see what we expect to see. This is my form of, my vision of your car, or my version of your car. So this is what you see here. So of course many of you know already. So of course most of you, they haven't seen it before. It takes some time to figure it out. So how many who haven't seen it before see something here? All right, if I tell you dog, or maybe a Dalmatian dog or something, then after a while, I mean, you'll see it. It's right here. I mean, it's not very clear, but it's there. And once you see it, you can't get rid of it. It's there. This one is a new one I got during the last summer. What do you see here? I have it. Somebody said something, but anyway, anybody is willing to guess? Okay, so landscape, mountains, hills. A woman, yeah, okay. Usually a man is the one who says that. There's a nude woman here, the back of a woman. Okay. You don't see it. Once you see it, you can't get rid of it. So this is just examples of what Ronnie was already trying to say. We see what we expect to see. We first guess, we first create this hypothesis about our perception, and then we test it, and this is a lot more efficient. One of the main themes of this course, at least as far as I'm concerned, is to show that this is also true for music. We hear what we expect to hear, and we enjoy it when we expect it, and we enjoy it even further when we don't expect it, but then figure it out by some sort of escalation or improvement, or what we call refinement of predictions. How can we explain it? How can we measure it? These are the kind of things that all of us want to tell you about. Okay, so this is again the story of reverse hierarchies. I think I'll keep this story. So again, going from the details to the main picture, or going from the top down. This is a famous figure from a paper by Merab Achissar and Charles Hochstein, but the whole thing was actually predicted theoretically by a computer scientist, theoretical computer scientist, John Tossos, in 1990 already, who said vision cannot work that way. It must have a component that is first predicting and then testing. We argue the same is true for auditory system, but I'll let Ellie go with this picture and so on. Okay, I'm sure you have it. All right, so this is my part, and of course the details will follow. You want to take a break, or we just?
No. Okay, we're taking a 10-minute break.